This is chapter 5, looking at the second law of thermodynamics. So things that we're going to be looking at here is that there's usually an imbalance between two systems. So there's some work that can be lost. We can't transfer all the heat to work. So we have two questions. What is the maximum amount of work that can be obtained theoretically? And looking at the efficiency. What's the max efficiency? So those are some things that we're going to consider with the second law. Here's our learning outcomes for this particular chapter. We're going to look at the second law. The Kelvin cycle is going to be probably the next set of videos. So we're going to concentrate right now on the alternate statements, okay, for the second law. You know, one thing that we have talked about so far is the conservation of mass and energy, right? This basically, when we look at this, is our first law. And that's our first law of thermo. And when we consider that, right, mass cannot be created or destroyed. It does not tell us basically whether a process can actually occur. It just tells us how much energy can be produced in the process, or needed in the process, but it doesn't tell us if it can actually occur. That's where the second law comes in. The second law tells us whether a process can occur in the direction it is given or not. So for example here, when we set our coffee cup on the counter, heat naturally goes from the coffee cup, which is hot, to the surrounding air, which is cooler, right? We know that it occurs, and because we always know that heat flows from something high to something low. But we can also look at the first law and calculate how much heat would flow from the surroundings into the system. Now we can calculate that quantity, but that doesn't tell us if the process can actually occur, which we know it cannot. So that's where the second law comes in pretty much. So when we look at various aspects of our second law, it's going to help us with the direction of the process, conditions of our equilibrium, and we're going to also find our theoretical performance, the best theoretical performance, by taking out what we're going to call irregularities. So, what we can maximally find, and then what we can actually, compare it to our actual. And that's when we are doing our evaluation, we're going to always predict the best, and then we know it's going to look at the actual and look at the difference. The other thing from the second law of thermodynamics, we can define our temperature scales like Kelvin and Rankine. And we're going to evaluate some various properties like internal energy and enthalpy. When we need to define a couple of terms, again, thermal energy reservoir, and it's a body of heat. And if it's supplying the heat is coming from, and this is going to be like our surroundings into our system, that's considered a source. If the heat is going from like the systems into the surroundings, that's called a sink. So if our thermal source or supplies the heat, that's our source. If it absorbs the heat, that's our sink. Okay. So you can think of general examples of thermal energy reservoirs is our ocean system in our atmosphere, right? Thinking about our atmosphere, this is a huge body. So when we think of a reservoir, we think of a reservoir that no matter how much a system is giving off heat or taking in heat, the amount of energy in our reservoir doesn't really change all that much. Okay, so our atmosphere can be a reservoir, and our ocean can be another reservoir of heat. So we can transfer work in between the two. And it can be compressed liquid going through our two phases. We can have two phases present also. Another way to think about it is the air in the room. So if we look at, and we have basically like a television in our room, and we know the television will give off some heat. Well, the air in the room is so large a reservoir that the amount of heat that the television is giving off is so small compared to the temperature in the room, or that the amount of energy in the room, that we don't see a huge temperature difference from the heat given off by the television. So that's what we think about a reservoir, is this huge source of energy that can either be put in or given off, but the source itself will not change all that much. So another thing that we need to be considering when we look at entropy and so forth is our heat engine. And where our heat engine, we take our high energy source and we put heat into our system. So our heat engine is our system, and so it gets energy from our high temperature reservoir. Some of it goes into work, and the remaining heat goes into our low temperature reservoir. And then it's a cycle, so we'll have another way to get some of that energy from back up, like our working fluid, back from a low reservoir back up to the high reservoir. So we have another source in here. So we're going to think of it as a cycle. So for example, here is a heat cycle where we have energy going in here, Q going in. Our fluid is moving where it's warm to the turbine, so some of that heat is going converting to work. The remaining fluid is going to the condenser, where we're going to take out the heat into our low temperature reservoir, and then we take our fluid and put it through a pump where we have work going in to go back to our cycle, to complete our cycle. This is an example of a power cycle. Just recall from before, this is a bit of review where we have our heat cycle, or heat in minus the heat out, divided by the heat going in, is our thermal efficiency. And our thermal efficiency is always less than can't be more, right? It's not equal to 100%. It's always less than 100%. This is looking at our performance, and we're always going to look at, when we calculate this, we usually calculate the max, okay? And because we don't have all the heat converting to work, some of the excess heat goes back into our second reservoir. Our maximum amount of heat efficiency is about 40%, okay? So if we look at automobile engines, that's about 20. Diesel engines gives us a 30%. Steam power plants are around 40%. Let's look at this example here. Here we have our heat engine. We're transferring heat, 80 megawatts into our heat engine, and some of it is coming out as our work, our power, and then our residual heat coming out is 50 megahertz. And so if we're asked to find our net cycle here, the power, recall that is our heat in minus heat out. And so if we have heat coming in as 80 megawatts and we have heat going out as 50 megawatts, our total net cycle is going to be 30 megawatt. Okay, that's how much power. And then if we look at our thermal efficiency, net power divided by the heat going in are 30, and the heat going in is 80 megawatts, and this comes out to be 0.375. So in this particular heat engine, we have about a 37.5% efficiency, thermal efficiency. We're going to look at the second law of thermodynamics in various statements. There's not one way to simply state our second law. So we have a combination of three. So the Kelvin-Planck and the Clausius statement, we're going to look in at chapter 5. We're going to talk about there. Our entropy statement, we're going to look more in chapter 6. So the Clausius statement, as we're looking at here, is that if we're operating between two temperature reservoirs, heat naturally flows from, this is possible right here. Heat naturally flows from a hot source to a cold source without any work. It just goes ahead and does that. But to flow energy from a cold source to a hot source, you need to apply work. So this is not true. We can't go from cold to hot. We always go from hot to cold. Okay? This one is impossible. We're looking at our Kelvin-Planck statement, and here we have just one thermal reservoir, and heat is being given to our system from our thermal reservoir, and all of it is being converted to our work, and we don't have a second a cold reservoir here to get for any residual heat. So here we're having complete transfer of heat to work, which we also know is very much impossible. So that's a Clausius-Planck. So if we violate either one of these statements, we basically violate the second law of thermodynamics. The last one here is when we're looking at our thermodynamic statement. It is impossible for any system to operate in such a way that the entropy is destroyed. So for example, here we have milk and coffee, and it will naturally start to mix on its own, and we're going from something that's very low in entropy to something where it's completely mixed, very high in entropy. On its own, this will not go back to this form at all. We cannot destroy entropy. So when we look at our entropy change of our system, and this is in some time interval, this is equal to the net amount of entropy into the system over some time interval, and that is also going to be equal to our entropy produced within the system over some difference in time. This term here is always can never be negative. It can either be positive or equal to zero. It's never negative. We cannot destroy entropy. So the system itself, irreversibilities. We cannot go from something that's totally mixed to two separate ones already. So for any system undergoing a thermodynamic cycle while exchanging energy, the transfer of heat from a single thermal reservoir, we can only give net work will only be negative or zero. It cannot be positive because there's no way to bring that mass up without applying some work or having another source. And so when we look at our net cycle, and we have no, and when we talk about, and we're going to talk about irreversibilities in the next chapter, but if there's no irreversibilities present, then it's going to equal zero. But if there's some internal irreversibilities, then our net, our cycle can only be negative. But let's look at our Kelvin-Planck statement and our Clausius statement. If we violate one, we violate the other statement. So let's consider this combination here, this system here, where we have a thermal reservoir here and we have a cold reservoir. If we only look at their left half, we see that we violate the Clausius statement because we're taking heat from a cold source to a hot source. So if we violate this, it's going to violate the Kelvin-Planck statement, that if we take our heat going from here, applying it to work, to our cold source, and we take that same amount of heat that we put into the cold source and bring it back up, we can't do this and still have this work. So if we violate the Clausius statement like here, then we violate Kelvin-Planck. The same thing here, if we look at just the dotted part here, if we have heat going in and then we have it transferring to work, well, right now this is set up where we have a cold reservoir, but the cold reservoir, the amount of heat going into the cold reservoir is also leaving. So basically we do not have a cold reservoir. So it's basically looking like we have our hot reservoir here, and that's going into our system, and all of that is coming out as work for our cycle. We're missing that cold reservoir, right? Because the amount of heat that's going in is also leaving. So we have no cold reservoir. So this is impossible. So we're violating our Kelvin-Planck statement if we look at this combination. And so if we violate the Kelvin-Planck, we violate the Clausius statement, because we need that Clausius statement to make this true, but that's we can't have it go out both directions. And this is where we'll stop, and we'll talk about the next bit will be with irreversibilities.